department in India as far as environment science is concerned. We are very near to the airport, so everybody is invited. You are most welcome. Hardly 25 minutes away from the airport. As far as my group is concerned, we are working in different aspects of the environment, mainly water, wastewater quality monitoring, assessment, remediation, developing many materials, adsorbent, nano-adsorbent. Then one of the focus is biorefinery. You already have the idea about that in the previous presentations. And then currently we are working on this biochar concept to deal with the soil fertility and climate change mitigation. As far as my publication are concerned, so I did not publish too many papers, but hardly 150 plus papers. But the good thing is I am getting a lot of citations, so already crossed 55,000, H factor of 89. So those who are working in this area, I think they have to look for the new thing, new concept to get better publication. My focus is on the biomass burning, which is one of the area, like especially in Delhi, we are having problem in winter, lot of smoke, lot of contamination. Though it is not like the only contributor as far as the air pollution is concerned, but we have to deal with this biomass burning. And in India, we are having about 600 million metric tons of this biomass, and out of this, I think 20-30% we are using for different purposes, and rest of the biomass we are burning in the field. It is not like, especially in Punjab or Haryana, if you see the whole India map, this biomass burning is taking place everywhere, whether it is north, south, east or west, but because of the climatic condition and many other factors, we at Delhi, we are having a lot of problems in winter. Also, this is not only restricted to India, we have this biomass burning everywhere, whether it is US or Europe or South Asia or China, you have this biomass burning. So if we can convert this biomass into some useful product, then we will be able to, reduce the emissions what we are getting when you do this biomass burning. So in India, especially in Punjab and Haryana, we have this in winter. So usually farmers are burning in the field, getting a lot of smoke in the air. And also, if you look into the contributors as far as the air pollution is concerned, let's take 1 ton of stubble. If you burn it, you will be getting about 2 kg of SO2, 3 kg of PM, particulate matter, both 2.5 and PM10, 60 kg of CO, 1460 kg of CO2, and 199 kg of air. So huge contaminants we are putting in the environment. Not only that, we are also losing the soil fertility from the top soil. We are losing about 339 kg of nitrogen, phosphorus, potassium, sulfur. So this is one example. We have a lot of other problems also. But why farmers are burning this? Because of many factors. One of the factors is the social factor, where we have the labor shortage. Second is, we have very small, time window between one crop to the another crop, and in this 10 to 15 days, we have to complete the harvesting, and then we have to keep the, agricultural land for the next crop. Lot of political problems, technological issues, financial issues, and many miscellaneous problems. And if we are not able to deal with these problems, I don't think that we are going to stop the biomass burning. So usually everybody is familiar now. We have 3 platforms. So many speakers were talking about the ethanol, bio-oil, gasification, biochar. So you can take any platform, especially we are working on this thermal conversion platform. You can also use this biological conversion platform where you can go for fermentation to ethanol or digestion to the biogas. And then you have mechanical conversion where you are dealing with the, some mechanical aspect as far as the biomass is concerned and converting that into biodiesel. So mainly I will be talking on the pyrolysis and this slow pyrolysis specifically in the today's lecture. So if you take any biomass, any waste, agricultural waste, sawdust, whatever biomass or agricultural residue you have, either you can convert that into liquid called bio-oil, we already have the lecture in the morning session, or you can go for the gasification. Finally, we are dealing with the energy. But our aim is to convert that into biochar, because biochar is a porous material, because it is having high surface area. So this can be used to remediate contaminants from the water. Maybe you can use that in the soil to improve the soil health. And finally, whatever you are putting in the soil, equal amount of the carbon you are sequestering. I will be coming to that. So overall, this is a very useful product. Keep in mind, when we are doing the biological conversion, the problem with the biological conversion is we need wet biomass. So you need to add some water to make it wet if it is dry. But in thermal conversion, we need dry biomass. At this point, when I said dry biomass, that means less than 10% moisture. So you will be getting the biochar or bio-oil, means you have the possibilities of getting multiple products. It is a very fast process, but if you take the biological conversion, it is a very slow process. You take several hours or days to complete it. So finally, you can play with the temperature and the residence time to get or optimize the yield. Let's say you are doing fast pyrolysis, go for the moderate temperature. You will be getting that process completed in 1 to 2 seconds. Maybe there is a possibility you can achieve up to 75% liquid plus some biochar and some gases. If you go for the slow pyrolysis, in literature or whatever we have done, we are not able to get more than 40% of the biochar. Rest of the gases, either you can just leave it in the environment or you can recycle to run the reactor you have. In gasification, mainly you have the syngas, but you also getting some char that is maybe around 10%. If you optimize or design the reactor in a better way, you may reduce that, biochar and liquid. So overall, this is a fine-grained charcoal, high in organic carbon, and largely resistant to decomposition. This is the key as far as the biochar is concerned. The half-life of this biochar is about 1,400, but again it depends how you are making, what is the characteristics of the biochar. So overall, if I summarize the properties, it can do carbon sequestration, high surface area, good water holding capacity, stability is more than 1,000 years, efficient absorption you can do. You can also increase the microbial activity when you are putting in the soil, enhance plant microbial interaction. Also it can stop leaching when you are using in the soil. So overall, our aim is to deal with the carbon cycle. So what we are doing is, let's say you have plant, so plant is taking this CO2, and when plant died, all the CO2 or nitrous oxide or methane going back into the environment. So this is your carbon neutral cycle. So if we can take some of the biomass out of this cycle and convert that into soil and keep it in the soil for thousands of years, so then we will be able to convert this carbon neutral cycle into carbon negative cycle. So this is basically the aim of this work. Now, there are many, paper in the literature, and most of the time, like when you are hitting something, you will be getting some black material. But technically, whatever you are getting does not mean that it is a biochar. You have to first identify, especially for the young researchers, if you are calling the final product to be a biochar, you have to look into many technical aspects, especially the H by C and O by C ratios. If your material is having less than 10% organic carbon, right, that is not going to be called as biochar. If it is having H by C ratio more than 0.7, it won't be classified as biochar. Or if the O by C ratio is less than 0.7%, we classify as biochar. So most of the time we are missing that, and lot of papers where this hydrochar is also being classified as biochar, that is not the biochar. I will be coming to that little later. Now, depending on the H by C and O by C ratio, you can also estimate some of the, approximate half-life of that particular product. If your O by C ratio is less than 0.2, the half-life is more than 1000 years. If the O by C ratio is between 0.0 and 0.6, the half-life is between 100 to 1000 years. If it is more than 0.6, it is hardly, less than that. So depending on that, you may classify your materials and accordingly you can use it. So in fact, there is a guideline you can find on the IBI web page. You all are familiar with the IBI, International Biochar Research Initiatives, where they classified what biochar you have to use in water or soil, especially a lot of data they have included in this table, especially for different type of soil, whether it is a clay soil or maybe sandy soil or sandy loamy soil. So accordingly you can select the type where you are going to use that. Now, why it is important? Because in 2018, IPCC recommended 6 technologies for the carbon sequestration, and out of the 6 technologies, I think I am not going into that detail, but if you see this recent paper published in 2024, there are 6 technologies which they have compared. If you see this data, out of whatever share you sequester, CDR method remove much smaller, maybe 1.3 million tons of CO2, or you can say less than 0.1% of the total carbon dioxide removal. And whatever method you are using, whether it is BE, CCS or biofuel or many other applications, out of that, biochar is the main player where you can see like majority of the, carbon sequestration is being done with the biochar. In other words, out of 6 technologies, whatever carbon you have sequestered, 97% sequestration has been taken place by this biochar only. This is the only advantage with that. Like weathering and other methods, what you have, they still have to prove the percent of carbon they are sequestering every year. So I am not going into that detail, but you can look into. Now, there are a lot of confusion also in the literature. Sometimes we are using char, sometimes we are using charcoal, sometimes we are using biocoal, sometimes you have this activated carbon. So let me try to differentiate a little bit among these terms. One is the charcoal. We usually, when we are using wood to convert that into the final product, we call it charcoal. If we use any material, including plastic, right, and we convert that into the product, we call that char. But when you are using the lignocellulosic waste and you are converting that into that particular product, we are calling it biochar. So keep in mind, this biochar that you are making, you have to finally look into H by C, O by C ratio. If you are not getting that in the particular range, whatever way you are preparing, whatever reactor we are not going to call that as a biochar. Now, how it is different from hydrochar? Because typically, hydrochar is having high H by C ratio, and that again does not qualify for the biochar. So those, especially the young students who are working in this area, they have to look into the technical definition. Now let me tell you how we started working in this field. In 2006, I was in US working in a project, in USDA project, converting biomass into bio oil. And from the bio oil, we were extracting the lignin-rich fraction and using as a wood preservative. We were catalyzing the bio oil inside the wood, doing the polymerization. So during this bio oil production, we got some this biochar. At that time, we were not knowing it is a biochar or char, but we tried to use that for the water remediation. And in 2007, we published this first paper. Our group published this first paper, where we used this for arsenic, cadmium, and lead removal. This was the start when we published this paper for the water, sector. After publication of this, we also published 2-3 more papers in the next 2 years, and then there was an exponential rise. And now if you see the literature, you have this more than 3,000 or 3,500 publications per year. So 20K or 25K publications you will get if you look into the Web of Science data. So this is just for your information. Now we started this making this bio oil with the auger-fed reactor. That was the indigenously designed reactor, where we were able to play in the temperature window between 400 and 500 degrees centigrade, and residence time was like between 0.5 to 5 seconds. At that time, we were interested to do the fractional, condensation to separate some of the chemicals. If you are interested, you can collect from each condenser and later you can mix all those together and use as an energy source. But our aim was to get that lignin-rich fraction out of the, bio oil to use as a wood preservative. So this was the actual reactor we were working at that time. Later on, we, upgraded this to the capacity of 7 kg per hour, where we were able to produce about 2 liters per hour of bio oil and 1.5 to 2 kg of biochar. The temperature window for this reactor was 375 to 500 degrees centigrade, and the residence time was 20 degrees centigrade. So if you are interested to make more biochar, increase the residence time, or if you are interested to make more bio oil, reduce the residence time. At that time, we were in collaboration with a company in Alabama. So based on our data, they designed this mobile type of reactor. So in place of bringing the biomass to the reactor, they were taking this, mobile reactor to the field, converting that into bio oil, and you can then transport the bio oil to any other place. I think this is much easier way to deal with that. Recently, I was meeting with our minister, Honorable Minister, Mr. Nitin Gadkari, and we had a very long session on the biochar application in the soil, and he was talking that especially in Maharashtra, we are losing lot of organic matter. It should be what he suggested about 0.8 or 0.7, but he was telling that it is now less than 0.4. So if we can increase that somehow to that level, I think we will be having the soil fertility back. And he was emphasizing to use the bamboo. So if we can convert that bamboo into biochar and use that in the soil. So based on the feedback what we got, we designed 2 reactors, especially for the poor farmers, because we are having only small farmers, so they cannot handle or they cannot take the biomass to that particular industry and give that free of cost. Either you have to collect or you have to give some incentive. So this is basically kacha and pakka reactor. So basically what we have suggested is, we already have the patent for these 2 items, that you have this clay soil in your agriculture field. You use that to make the clay this reactor. Only thing you have to play with how to deal with the oxygen content inside. So we optimize that, and we are giving lot of training to the farmers also. Also they can make the pakka reactor using brick and also the concrete at the community level, and then at the community level they can also convert the biomass into biochar. The beauty with this reactor is, once you are done in the field, you dismantle it. So when you have clay with biochar, you have better productivity. We established that, we published a lot of work in that area. So biochar, when you characterize, you have all sort of pores, mesopore, micropore, ultrapore. I'm not going into the detail, but you can also manipulate the surface, of the biochar. So we are doing that by modifying the surface, bringing a lot of new, groups which can take specific contaminants out of the water. And when we are doing that, you can play with either of the factors. I summarize here. Maybe you have chemical composition, maybe you have bamboo, you have agriculture residue. So that will result into different products, different characteristic of the biochar you will be getting. Then temperature, heating rate, mass transfer rate, residence time, oxidative conditions, pressure, type of the input, catalyst. So many things you can play with and converting into the required product. I am not going into that detail. But there are two ways to manipulate the surface to make, specific biochar for specific contaminant or specific, application. One way is to do the treatment with the feedstock. We are doing that. And then do the pyrolysis to get the final product. So when you do that, I think you have better stability of the product. Second thing is you convert that into, biochar, and then you do the treatment or surface modification. That way you will be able to make the biochar specific for particular contaminant or particular application. So in this connection, we developed some magnetic biochar. We dispersed some iron nanoparticles on the surface of the biochar, and we try to make it magnetic. Why? Because at that time we were interested that this should be used especially in our arsenic contaminated area, especially in Bengal, where they have very sophisticated, treatment plant, but after few days or few months, those are not working. So what you have to do is, we can make a tank at the community level. You disperse that magnetic biochar in the tank. Take that in the morning by using a simple magnet, and your water is ready for the drinking purpose. So that was the aim. So we had conversation with one of the industry. I think they are in the process to do something with this biochar. So whenever you are developing that, you need lot of characterization. I am not going into that detail. You already have the idea about that. So lot of information you will be getting. Finally, if somebody is interested to get more information about this, biomass, characterization, manipulation, type of reactor, residence time, how to play with the condition, we published at that time one review article in 2006 in Energy and Fuel, and so far this has been cited more than 7,000 times. So in any document, whether it is a patent or government document from UK, US, you will find the reference of this article. So I feel now, very proud that at that time we have written, and now this is a reference for those who are starting work in this area. So my group is working in water filtration, in soil management, and also in the food security. So I will briefly give you some idea what we are doing, though it is very difficult to cover each and everything. So we developed some of the biochar by using different materials like pine wood, oak wood, pine bark, let's say energy cane, corn stover, then you have rice husk, wheat husk, oak stem. So we have screened many agricultural byproducts. Let me tell you, we are not interested to use the wood, because that is not the way to convert into biomass or to deal with the climate change mitigation. How to use the agricultural byproducts, that is basically our aim, especially as far as the Indian government perspective is concerned. So you can use this biochar in 4 different ways. Once you develop, manipulate, you do everything, you will be able to use that in 4 different ways. First is we are making cartridges using the biochar. So you can simply use in the filtration unit, and in the filtration unit you don't need any electricity, so you just pass through the water through this cartridge. Then we can use this as a magnetic biochar. Then we also developed some biochar bags. We patented that. So like tea bags, you can use this biochar bags. Maybe in the bucket you can drop one, big bag to decontaminate arsenic, and maybe in the morning you will be getting free arsenic-free water. This is where you can make some flotation balls, cages, like we have lot of contaminants in Yamuna river, in many water bodies. So this is the way how you will be dealing with the, those contaminants if you want to remove from the river or from the other bodies. So these are some of the possibilities I am exploring. Also, like if you take into account the CO2 sequestration, so we calculated, it is also reported in the literature, if you have 1 ton of biochar, you will be able to sequester about 3.66 tons of CO2. So let's say, I'm just giving you one example. If your biochar is having 90% carbon, this is what somebody discussed in the morning, and you are using 10 kilogram of biochar, let's say you use that in the soil, so you will be sequestering 9 kilogram of carbon, and this 9 kilogram of carbon is equivalent to 33 kilogram of CO2. So you can just use the simple conversion factor, you will be able to get it. So it's very important. When you use in the soil, you will see, a lot of changes. It increases the nutrient availability, microbial activity, soil organic matter. So I discussed that. I'm not going into that detail. Now recently, I just want to give you one idea. Recently, we used this biochar to deal with the nitrate contamination in the water, because we have many places where we are using this, nitrate removal. So when you do that, what you are going to do once your carbon is loaded? So again, then you will be going for regeneration, desorption. That is not the very cost-effective method. Finally, you have to dispose the biochar. So what we have done in this case, after the adsorption or removal is over, we took this, biochar, which is loaded, which is not loaded, which is also having some urea, nano-urea, we mix in a different proportion, and then we use that in the soil. So we did soil amendment. So our aim was to replace this urea by this organic fertilizer, because you already have the biochar having lot of nitrate on that, you have lot of nitrogen. So once you use in the soil, maybe you can reduce the application of the, this inorganic fertilizer. So very good, very encouraging results we have obtained. These are some of the amendments on the plant growth. This is the chili plant. You see, this is control without any biochar. Then this is with urea. This is purely with the biochar, no nitrate loading. And this is after the nitrate loading. You see the plant growth. And finally, we have carried out the, fruit, when you have the plant growth is over, how the fruit quality is changing, how many fruit you are getting per plant. So we carried out this, like in control, no fruits. In urea, we have only 1 fruit. Now this is the best optimum condition, where we are using 2% of nitrate loading biochar in the soil. Maximum length means the fruit quality as well as the number of fruits. Excellent results we are getting. Now recently we started using this material for the per and polyfluoro, substances. I don't know how many of you are familiar with. This is one of the emerging area, especially in US. I think probably 90% water is contaminated with this PFOS. Recently, EPA issued the guidelines where the permissible limit is only 40 ppb parts per trillion. So sooner or later we will be dealing with the same problem. So somehow you have to play with the biochar, engineering, and then accordingly you have to see whether you are dealing with the short chain PFOS or the long chain PFOS, and you can manipulate the surface and remove those contaminants. I don't know, PFOS is basically coming from when you have non-stick fry pan. I think don't use that. Even if you have one scratch, lot of PFOS is coming into the water, into your food. That is one source. Second source is your, this packing material, especially the food delivery boy, whatever he is supplying or she is supplying, that is the material having this PFOS. So try to use the iron, or steel in place of this non-stick fry pans or non-stick cookware. This is one of the emerging area. Anybody can explore. Now we have also developed some floating bed. We changed engineered the biochar in a way that it will be like hydrophobic. So when you disperse that biochar, it will form a mat. Once it will take the oil, you can take it by skimming, and then you can convert that into some sort of barricades, or maybe you can use as a fuel. So this is one of the area where we are working. Now, why we are using this biochar? Because this RO system is not which is recommended, especially if you are getting the water, surface water or municipal water. I don't think RO is very much required. Nowadays, this becomes a fancy item. Even if your TDS is 250 or 300, I think you all are using the RO. I will suggest not to use that RO until unless the TDS is very high. Because whenever you have the advertisement, nobody is telling you what should be the minimum level of calcium and magnesium. So until unless you achieve that, I think that RO is going to take all the minerals out of the water. But in this case, when you have this biochar, I think you are fine with that. Required minerals will be available in your drinking water. So that is what we are trying. Even our NGT, they basically ordered that recovering 75% of the water is mandatory, because in RO you are only getting 20-25% of the water, rest is going into the drain. So until unless you have very high TDS, you should not be using this RO system anymore. Recently we also used this biochar in the constructed wetland. So we carried out some experiment in our garden. We collected water from one of the hostel, and I'm not going into the detail, I'm just showing one slide. So you can see that when you have biochar and when you do not have biochar, how the your plant is growing, and also the quality of the water is improving. So we will be publishing this very soon. We are also converting into nano biochar and using this for different applications. So this is one of the areas where we are working. And finally, I think, without going into the detail, I will just highlight that we did some experiment on the carbon sequestration. We have a setup in the lab as well as in the garden. We have these simple, setup where you have soil with biochar, and we estimated how much CO2 is coming out with time, and then we try to see how this is equal to what we are getting from the garden. So this is one of the, I think, research area where my group is working. We were using efflux analyzer to determine this CO2 in the field as well as in the lab. So this was the setup. I'm not going into the detail. So when you use this, biochar, and when you use this biomass, you will have more than 90% reduction when you are using the biochar compared to biomass. Because biomass is going to go for the degradation, and you will be ending up whatever you have as I explained in the carbon neutral cycle. So this is one of the study. We published this. Then we carried out all the analysis of the soil before and after the treatment. And the beauty, you see here, the water holding capacity of the control is only 11.2 by weight percent. It increases to 29.7 when you are adding the biochar. The cation exchange capacity from 4.6 to 36.08. So huge increase. So we are trying to use this in a way that the biochar is going to release those nutrients slowly. In other words, the slow release fertilizer we are looking into. Right, so whatever I am showing here as far as CO2 sequestration study is concerned, this is already published and available in RSC Advances. If somebody is interested, I will be happy to give you the paper. This is another work where we use this biochar to decontaminate. I should not say decontaminate, immobilization of the metals in the soil. So what biochar is doing, when you use that in the contaminated soil, it is converting the bioavailable fraction into non-bioavailable fraction. So those will be like not available in the to the plant, so you will have like no toxicity in the plant or fruits. So with this, I think we are also testing this, because now government is putting a lot of emphasis on the use of nano urea. So now we are testing this biochar with urea, with nano urea, with combination, and many other combination we are making and testing. These are some of the results we have from the nano urea. So we are also giving training to the farmers, going to villages, to Ministry of Agriculture, and we are trying to tell them that make the reactor and use it to make the biochar. Now, if you are making biochar, you have to have the certification. Just for the information, either you can take the certification from the IBI, or you can go from the European biochar certification, and then you are able to make your product in the public domain, or you can bring that in the public domain, but you need that. So far in India, we are not having any certification like IBI or the European. Recently, we published this book, so we have given a lot of information about the development of the biochar for the water and wastewater treatment. You will get a lot of examples, problems in the book. So those who are beginners, I think they should start looking into the problems we have given at the end of the chapter. This is having about maybe 15-16 chapters answering to all the problems what you have in your mind, covering all the contaminants, including PFOS, wetland and everything. So this is published by Elsevier in recently 1 year back. So this is all about what I was thinking to explain. Now,
Long live India and France friendship.